Hi, this is part 1 of week 28 of AP Physics, and we're going to go ahead and wrap up unit 7, which is torque and rotational motion. For our agenda, we're looking at angular momentum, and then we'll do some practice problems. So for our lesson objectives, students will learn how a radius affects angular momentum. We're going to begin with angular momentum. The angular momentum of a rotating object is given by the following equation, which is L equals I times W. Actually, that's not a W. That is Greek letter omega. And for the L is the angular momentum of an object, which is measured in kilograms centimeters squared over seconds. I is the moment of inertia of the object, which is measured in kilograms centimeters squared. And finally, the omega is the angular speed of the object measured in rads per second. Angular momentum is related to torque in the following equation, where the net torque is equal to the change in angular momentum over the time interval. So it's going to be delta L over delta T. And that could be used to find the torque of an object, such as that in a picture of a merry-go-round. The angular speed of a rotating object can be found using the following equation, where angular speed is equal to 2 multiplied times pi multiplied times frequency. Now we know that frequency is the inverse of the period, so we can go ahead and modify this formula to have the angular speed be equal to 2 multiplied times pi divided by the period of the rotating object. If the net external torque acting on the system is 0, the total angular moment of the system is constant and is said to be conserved. So Li equals Lf. This is known as the law of conservation of angular momentum. This type of problem can be solved using the following formula, which is have I, which is moment of inertia, multiplied times the angular speed initial, is equal to the final I times angular speed. Now, this formula is used to figure out what will be the angular speed of an object, and the object can change its angular speed by changing its distribution of mass. For example, you see the high diver on the left picture. The high diver, as they jump off the diving board, they're going to go ahead and tuck themselves in, reducing their radius. That's going to go ahead and give them more angular speed, so they'll rotate at a faster rate. The same can be seen for the ice skater. The ice skater goes ahead and spins. As they draw their arms in, they're going to go ahead and increase their angular velocity, their angular speed. And as they move their arms out, they're going to go ahead and slow down their angular speed. Going back to the diver, as the diver comes out of the tuck position and they essentially move their mass further out from the center of rotation, they're going to go ahead and slow down their rotation and hopefully go into the water fully vertical. Now let's go ahead and take a look at example 8. In example 8, we're asked the following question. A student sits on a pivoted stool while holding a pair of weights. The stool is free to rotate about a vertical axis with a negligible friction. The moment of inertia of the student, the weight, and the stool is 2.25 kilograms centimeter squared. That is our initial moment of inertia. Let me go ahead and write that down. 2.25 kilograms centimeter squared. Next, the student is said in rotation with arms outstretched, making one complete turn every 1.26 seconds. That is the period. So I'm going to write down period is equal to 1.26 seconds. Then in part A, they ask you, what is the initial angular speed of the system? So the initial angular speed, we're going to go ahead and use this formula for part A, which is angular speed, in this case initial. It's going to go ahead and be 2 pi over the period of revolution, which is 1.26. So we'll substitute that in to get our initial angular speed. It's going to be 1.26 seconds. Plug it into the calculator, and we get the following answer. 2 times 3.14 divided by 1.26 gives us 4.98. We'll go ahead and round it up to 5 rads per second. That's part A. In part B, they ask you, as he rotates, he pulls the weight inward so that the new moment of inertia becomes 1.8 kilograms centimeter squared. What is the new angular speed of the system? All right, so our inertia changed because the weight distribution changed, and now it is 1.80 kilograms centimeters squared. So they're asking what will be the new angular speed. The initial one we have right here at 5 rads per second. All right, so we're going to go ahead and use this formula for the law of conservation of rotational momentum. So it's going to go ahead and be Li equals Lf. All right, so initial equals final. And let me go ahead and what is L? It is inertia multiplied times angular speed, final and initial. All right, so we're looking for this one, so I'm going to go ahead and divide by I on both sides. It's going to be IF, cancel that out. And there's our formula. It's going to be moment of inertia initial times angular speed initial divided by moment of inertia final, and that's going to go ahead and give us our answer. All right, so let's go ahead and do the work for it. That's going to be I initial was 2.25 kilograms times meter squared divided by, or multiplied times I initial, which was 5 rads per second, divided by the new moment of inertia, which is 1.80 kilograms times meter squared. So we end up with the following, which is 2.25 times 5 divided by 1.8 gives us 6.25 rads per second. All right, so that's our answer for part B. Here's part A. Next, in part C, we're asked the following question. Find the work done by the student on the system while pulling in the weights. All right, so the work done by the student, we're going to go ahead and use the following formula. Work equals change in rotational kinetic energy. All right, so we're going to go ahead and plug all the values in and solve for that formula. So this will be part C. So work is equal to change in rotational kinetic energy. So therefore work is equal to kinetic energy final minus kinetic energy initial for rotational kinetic energy. And the formula for rotational kinetic energy is 1/2 moment of inertia I multiplied times angular speed squared. So it will look like this. Work is equal to 1/2 I final times angular speed final squared minus 1/2 moment of inertia initial times angular speed initial squared. Those are our values. So we're going to go ahead and plug them in and solve. So it's going to go ahead and be 1/2 moment of inertia final was 1.8 kilograms times meter squared. Angular speed final was 6.25 rads per second minus 1/2 moment of inertia initial was 2.25 kilograms times meter squared, and angular speed initial was 5 rads per second, and that is squared. From here we're going to go ahead and plug it into the calculator, round it off slightly, so it's going to be 0.5 times 1.8 times 6.25 squared gives us 35.1 joules. Now on the other side, minus 0.5 times 2.25 times 5 squared gives us 28.1 joules. All right, after that we go ahead and subtract, and our answer, the work done by the student as he is pulling the arms in, is 7 joules. All right, that is example 8. Let's go ahead and now take a look at the next one. This one is problem number 21. It said, if the student suddenly releases the weight, will his angular speed increase, decrease, or remain the same? So I'm assuming at this point he has already brought the weight in. So all the mass is at the center. If he lets it go, the mass still remains at the center. So the answer will remain the same. So that will be problem number 21. Let's go ahead and take a look at problem number 22. In this problem, it says a star with an initial radius of 1.0 times 10 to the 8 meters and the period of 30 days collapses suddenly to a radius of 1.0 times 10 to the 4 meters. Find the period of rotation after the collapse. A couple of things we need to keep in mind. This planet is a solid sphere, so a moment of inertia is going to be 2 or 5 mr squared. And also for the angular speed, we can find it by multiplying 2 pi over the period. The period was given to us in days. We're going to go ahead and change it to seconds. So our answer will be in rads per second at the end. Alright, so now let's go ahead and solve for this one using the formula. Momentum times angular speed initial is equal to momentum times angular speed final. Now let's go ahead and substitute some formulas in here. First of all, we're we're going to go ahead and substitute the initial moment of inertia. So it's going to go ahead and be 2 over 5 capital M, and then the radius, the initial radius squared, and that's for the I. Now that's going to go ahead and be multiplied times the initial angular speed, which is 2 over pi, or 2 times pi over t initial, our initial period of 30 days. All right, so now the next part is going to be over on the other side. It's going to be 2 over 5 for the momentum final. So it's going to be m, our final has a new radius, and we're going to multiply it times 2 pi over t final, which is what we're solving for. The final period is going to be in seconds, the answer. All right, so now we'll look at this formula. There's a lot of stuff that we can cancel out from both sides because they are the same. So for example, 2 over 5, if you multiply both sides by 5 over 2, they'll cancel out. What else? The 2 and the pi, also the same on both sides, so we can also cancel it out. Divided by 2 pi on both sides, they're gone as well. What else can we go ahead and get rid of? The mass of the planet remains the same, so that one will also cancel out. Let's clean this up a little bit. It is really just Ri squared over Ti is equal to Rf squared over Ti or Tf. All right, and we're looking for Tf. All right, and so the rest of this problem, we can just go ahead and move stuff around to go ahead and solve for Tf. All right, so I'm going to go ahead and move it over on this side. It's going to be Tf is equal to Rf squared multiplied times Ti over Ri squared. So that is our formula after we go ahead and modify it. And we have all of these values. We can go ahead and plug it in and solve for what is the period of rotation of this planet. All right, Rf is the final radius. All right, final radius was 1.0 times 10 to the 4 meters. I'm going to square that. Multiply times Ti, the initial period of rotation was 30 days. So that is 2,592,000 seconds. And all of it is divided by Ri squared, the initial radius 1.0 times 10 to the 8 meters, and that is squared. All right, so now we just go ahead and plug it into our calculator, and we get our new period, which is the amount of time it'll take it to go ahead and complete one revolution. So it's going to be 1.0 times 10 to the 4th squared multiplied times 2,592,000 divided by 1 times 10 to the 8th squared. That gives us our answer of 0.026 seconds. So very quick period as this planet is spinning around. Up next, let's do part B of problem number 22. We're given the following. It says the mass of the planet is 2 times 10 to the 30 kilograms, and they want to know what is the work done by gravity when it collapses a star. So to figure out work is the change in rotational kinetic energy. For rotational kinetic energy, the formula is 1/2 I multiplied times angular speed squared. So let's go ahead and plug those in. So it's going to go ahead and be 1/2 moment of inertia final times angular speed final squared minus 1/2 moment of inertia initial multiplied times angular speed initial squared. That's going to be our setup. Let's flush out the formula a little bit. The I, it is a solid sphere, so it's going to be 2 over 5 mr squared. So let's plug those in. It's going to be 1/2 2 over 5 mr squared, and this is our final radius, and multiply times the angular speed final. Angular speed final is going to be 2 over pi over the period, and now that is our period final, and that is squared, so all of this will be squared as well. Next, for the initial, it's going to look much the same way. 2 over 5 mr initial squared, and that's going to be multiplied times 2 pi over ti, all of it is squared. Alright, so now we got our formula. We can go ahead and plug in the values and solve for this. So let's go ahead and do that. Work is equal to 1/2 times 2 over 5, so it's going to give us 1 over 5. 1, 5. The mass of this planet was 2 times 10 to the 30. The radius of the planet final was 1 times 10 to the 4, and that's going to be square. 1 times 10 to the 4 squared. Let me move this up a bit, give us some more space. Multiply times 4 times pi squared, and all of it divided by the period final. The final period was 0.026 seconds, and that is squared because we do square it there. Alright, so that is the left side of this formula. On the right side, we're going to have very similar 1 over 5 multiplied times m, same mass. The mass did not change. Multiplied times radius initial, which is 1.0 times 10 to the 8, and that is squared, and times 4 pi squared over the ti, which is squared. The initial period was this very large number, 2,592,000 seconds squared. Alright, so that is all the numbers we're going to go ahead and plug in. And now we're going to go ahead and reach for the calculator and plug all of this into our formula. 1 divided by 5 is just 0.2, multiply times 2 times 10 to the 30th, multiply times 1 times 10 to the 4 squared, multiply times 4 times 3.14 squared, all of it divided by 0.026 squared equals the following number, 2.33 times 10 to the 42 joules, minus, on the other side, we're going to go ahead and have 0.2, which is 1 over 5 is 0.2, times 2 times 10 to the 30th, times 1 times 10 to the 8 squared, times 4 times 3.14 squared, divided by 2,592,000 squared. It gives us the following answer, 2.35 times 10 to the 34 joules, and then we go ahead and we subtract 2.33 times 10 to the 42 minus our answer. It gives us 2.33, just about the same value. If we round it up, 2.33 times 10 to the 42 joules of energy done as the planet is collapsing. And that is part B of problem 22. In part C, we're asked the following. What is the speed of an indestructible person standing on the equator of the collapsed star? So after standing there and they're spinning around, how fast are they traveling? So let's go ahead and figure that out. The velocity is equal to radius times angular speed. Alright, now the angular speed is going to be 2 pi over the period. So let's go ahead and plug in the numbers here, and we can go ahead and figure out the velocity of a person. So the radius of the collapsed star, so the final is going to be 1.0 times 10 to the 4 meters multiplied times 2 pi, and all of it divided by t, the period, which is 0.026 seconds. Alright, so now we're going to go ahead and reach for the calculator and solve for this problem. So it is 1 times 10 to the 4 times 2 times 3.14 divided by 0.026. It's going to go ahead and give us a speed of 2,415,385 meters per second. Alright, we should put that in scientific notation. We'll just go with 2.4 times 10 to the 6 meters per second. And that is how fast that person will be traveling standing on the equator of a collapsed star. In example 9, we're asked the following question. A merry-go-round modeled as a disc of mass 1 times 10 to the 2 kilograms and a radius of 2 meters is rotating on a horizontal plane about a frictionless axle. Alright, so now a student with a mass of 60 kilograms jumps on the rim of the merry-go-round. The system's angular speed decreases to 2 rads per second. If the student walks slowly from the edge towards the center, find the angular speed of the student when she reaches a point of 0.5 meters from the center. Alright, so that is part A, and part B, we'll deal with that in a bit. So for part A, we're going to use the law of conservation of rotational momentum. So it's going to go ahead and be the moment of inertia initial times the angular speed initial is equal to moment of inertia final times angular speed final. Now that we have that, let's go ahead and start plugging in values. First of all, for the moment of inertia, there are two objects, the disk and the student. The disk, I'm going to put di, is really 1/2 mass times radius squared because it is one solid object, the mass is distributed evenly. But for the student, her mass is where she's at, it's not distributed everywhere, so it is mr squared. That will be moment of inertia. So for the I here is really two things, the disk and the student. So to figure out for the angular speed final, we're just simply going to divide by I on both sides. So it will look like so. And that will cancel out and giving us our angular speed final, which is what we're looking for. Now let's flush out this formula a little bit more. Here we have the I, which is really, again, the disk and the student. First for the disk, we're going to go ahead and put 1/2 mr squared. And that's going to be plus the student, which is lowercase m r squared. All right, multiply times the initial angular speed. On the denominator for final, this is all going to be 1/2 mr squared. It's the same for the disk. The disk does not change throughout this problem. Plus mr squared final for the final distance. That does move because the student is moving closer to the center. So that r does change from a 2 to a 0.5 since the student is moving closer to the center. All right, so that will be our setup. We go ahead and we plug in all of our numbers. We're going to go ahead and solve now. All right, so we're going to go ahead and put 1/2 m, that will be 100 kilograms, multiplied times the radius of 2 meters, plus m, that's the mass of the student, multiplied times her distance, initially was at 2 meters, all right, and that is squared, and enclose all this in parentheses, and that's going to be multiplied times the initial speed of 2 rads per second. All of it is going to be divided by the denominator. For the disk, that remains the same. So it's going to look the same, 1/2 100 times 2 squared plus, now the student's going to be slightly different. Although her mass remains the same, her position did move. She moved closer to the center. She is 0.5 meters from the center of rotation. So that will be the setup for this problem. After that, we're going to go ahead and plug in all our values. I'm going to go ahead and reach for my calculator and let's see, plug all of these values in. So it's going to be 0.5 times 100 times 2 squared. That's going to go ahead and give me 200 plus 60 times 2 squared gives me 240 over 200 plus 60 times 0.5 squared gives me 15, and all of it multiplied times our 2 rads per second. So our final answer will be 440 divided by 215 times 2 gives us 4.1 rads per second, and that is part A, 4.1 rads per second. In part B of example 9, we're asked to find the change in the system's rotational kinetic energy caused by the student's movement from 2 meters to 0.5 meters. So for a change in rotational kinetic energy is rotational kinetic energy final minus rotational kinetic energy initial. All right, so let's go ahead and plug in all the values for that. So it's going to go ahead and be as follows. For rotational kinetic energy final, it's going to be 1/2 inertia multiplied times angular speed final squared minus 1/2 inertia initial multiplied times rotational kinetic energy initial squared. All right, so that's what we got. Now for the inertia, remember that there's two objects, so it is the disk and the student. So let's flush out the formula a little bit more. So it's going to be 1/2, and we'll put in parentheses. Let's put in the disk first, 1/2 mr squared, and that's going to be plus the student, who's lowercase m r squared multiplied times the angular speed squared minus 1/2, here's the disk, mr squared, plus the student, mr squared angular speed initial. That is her initial radius and final radius, and the radius of the disk remains unchanged. So that will be our setup. Now we're going to go ahead and plug in all the values that we've got to go ahead and solve for this part. So it's going to be changing rotational kinetic energy. It is 1/2 multiplied times 1/2 times m. The mass of the disk is 100. The radius is 4 squared. No, the radius is 2 squared, plus the mass of the student 60 multiplied times her final radius, which is 0.5 meters squared, and that's going to be multiplied times the angular speed final, which was 4.1 rads per second squared. And all of this we're going to subtract it minus, now this side of the formula is going to be 1/2, and then the inertia of our disk plus the inertia of the student at her initial position 2 meters, and multiplied times her initial angular speed of 2 rads per second, and that is squared. Alright, now we got to go ahead and plug all these values into our calculator. So I'm going to reach for my calculator here and plug them all in. For the numerator, not the numerator, sorry, the left side, we're going to begin right there. So it's going to go ahead and be, just going to take it step by step. So it's going to be 0.5 times 100 times 2 squared. That's going to go ahead and give me 200 plus 60 times 0.5 squared gives me 15. Multiply times 4.1 squared. 4.1 squared gives me 16.8. All of it minus, on the other side it's going to be 1/2. And let's go ahead and plug everything in here. Let's see, we've got 0.5 times 100 times 2 squared gives me 200, plus 60 times 2 squared gives me 240. Multiply times 2 squared, that is a 4. Alright, so we got all of this. Now let's go ahead and do one final plug into the calculator and get our answer. So it's going to go ahead and be 0.5 times 215 times 16.8 gives us 1806, minus, on the left side we got 0.5 times 440 times 4 gives me 880, and these are in joules. Now we subtract 1806 minus 880 gives us 926 joules, and that is the change in rotational kinetic energy for the whole system. Alright, now let's go ahead and take a look at part C. Here they ask you to find the work done on the student as she walks towards the center. So just the student, not the disk. So that's what we'll be working on. So again, for the work, that is the change in rotational kinetic energy, but this time it's going to be just for the student. Alright, so let's go ahead and move along to part C next. So work is the same thing as change in rotational kinetic energy, which is rotational kinetic energy final minus initial. Alright, so that's work. So we're going to go ahead and begin plugging values in. So it's going to be rotational kinetic energy for the student is going to be 1/2 her inertia multiplied times the angular speed final squared, minus 1/2 her inertia multiplied times angular speed initial squared. Alright, so that'll be the work done by the student. Alright, let's go ahead and flush out the formula again a little bit more. M, what is the I? The I for the student is just mr squared. So I'm going to go ahead and put that in. And that is her final position. Multiplied times the angular speed squared, final. And 1/2 m times her initial position squared times angular speed initial squared. Alright, so that's going to go ahead and be the formula. Now we can go ahead and plug in all the values. So work equals 1/2 m. M is the mass of the student, 60 kilograms. Her distance from the center final is 0.5 squared multiplied times her final angular speed of 4.1 rads per second squared minus 1/2 mass of the student, 60, initial Distance, she was at 2 meters squared, multiplied times her initial angular speed, 2 rads per second. So there we have it. All right, from here we go ahead and we get our calculator and begins plugging them all in, and we'll see what we get. So 0.5 times 60 times 0.5 squared times 4.1 squared gives us 126 joules minus 0.5 times 60 times 2 squared times 2 squared gives us 480 joules for a grand total of 126 minus 480, negative 354 joules of work that the student did on the disk. All right, that is part C of example 9. In problem 23, we're asked, is the energy conservation violated in the above example? Explain why there is a positive charge change in mechanical energy and what's the origin of this energy. Well, no, it is not violated. There is an external force, and that is the student is doing work on the system, and that is why we have a positive change in mechanical energy. So no, there's no violation of the law of conservation of energy. In problem 24, we asked the following question. Find the angular speed of the merry-go-round before the student jumped on, assuming that the student didn't transfer any momentum or energy as she jumped on the merry-go-round. So for this problem, now our 2 rads per second becomes our final. We want to know how fast was the merry-go-round spinning before the student jumped on. So now we're looking for the angular speed initial. All right, we're going to go ahead and use the following formula to go ahead and solve this problem. Initial times angular speed initial is equal to moment of inertia final times angular speed final. So that's what we're looking for. So we want to isolate by dividing by I on both sides, the moment of inertia initial. So that's gone. So I'm going to go ahead and erase it. All right, and there's our formula. All right, let's go ahead and flesh it out a little bit more, put in all the values that belong to it. For example, the moment of inertia for the disk is 1/2 mr squared, as opposed to the moment of inertia for the person is mr squared. This one has a half, this one does not. So angular speed is equal to moment of inertia final. That's both the student and the disk put together. So it's going to go ahead and be, let's go ahead and put the student first. It's going to, well, let's put the disk first, 1/2 mr squared plus the student mr squared multiplied times the angular speed final, 2 rads per second. And this all of it is divided by the initial moment of inertia, initial before the student jumped on. So it's just a disk. So if it's just a disk, it is 1/2 mr squared. That will be the setup for it. Now we plug in the numbers and go ahead and solve. So it's going to go ahead and be 1/2. It's going to be, let's see, mass is 100, multiplied times the radius, which is 2, plus the student was 60, also standing at 2 meters. And that's also going to be multiplied times our 2 rad squared. All right, all of this is going to be divided by 1/2 mr squared. So that is just the disk that they're spinning on the merry-go-round, 2 squared. All right, so that's going to go ahead and be our setup. We're going to go ahead and plug everything we've got into our calculators and go ahead and solve. So let's see, it's going to be 0.5 multiplied times 100 multiplied times 2 squared. It's going to go ahead and give us 200. It's going to be 200 plus, we're going to add both of those together, plus 60 times 2 squared equals 240 multiplied times 2 rad squared. All divided by 0.5 times 100 times 2 squared, which is 200, and that's our setup for this problem. So our answer for part A is going to go ahead and be 200 plus 240, that's 440 times 2 divided by 200, which gives us 4.4 rads per second as our, that was the initial angular speed of the disk before the student jumped on. Next, let's go ahead and take a look at part B. They ask you, how much did the kinetic energy of the system change when the student jumped on? All right, so let's go ahead and take a look at that. So So it's going to be 4.4 rads per second. So how much did it change? All right, so for changing kinetic energy is final minus initial. So it's going to be rotational kinetic energy. It's going to be rotational kinetic energy final minus rotational kinetic energy initial. All right, so now we got that. We're going to go ahead and start plugging in all the values that we know for rotational kinetic energy. It is 1/2 moment of inertia times angular speed squared. So let's go ahead and plug in those values. 1/2 our final moment of inertia final squared minus 1/2 I initial moment of the angular speed initial squared. So that will be our formula. Now let's go ahead and work with the I. All right, the I is the moment of inertia. The final one has both the student and the disk spinning. All right, so that formula, we're going to go ahead and flesh it out just a little bit more. So it's going to look like this, 1/2. And again, final's got both of them. The disk, 1/2 mr squared plus the student mr squared multiplied times the angular speed final, that one squared. And then on here it's going to be minus 1/2, but the initial inertia, it was just the disk initially before the student jumped on. So we're just going to go ahead and put just a disk mr squared and initial angular speed square. So that's going to be the right hand side. All right, now we can go ahead and start plugging in values for this and get our answer. So that's going to go to be 1/2 m, the mass of the disk, 100 multiplied times 2 squared, plus the mass of the student, which is 60 at 2 meters squared, multiplied times the angular speed final, which was 2 rads per second, and that is squared. And it's going to be minus, here we have it, 1/2. Now it's just the inertia of just a disk, 100, 2 squared, multiplied times the initial angular speed of 4.4 rads per second, and that is squared as well. All right, so let's go ahead and plug in all the values into the calculator, and let's start getting the answer. All right, so it's going to go ahead and be 0.5 times 100 times 2 squared. It's going to give us 200, so I'm going to put 100, 200 plus 60 times 2 squared, it gives us 240, times 4, because that's the rad square is 4, minus, on this side it's going to go ahead and be 1/2, 200, and the 4.4 squared is 19.4. All right, let's plug in these numbers again into the calculator and start getting our final answer. So it's going to be 0.5 times, on both of those, 440 times 4. That's going to go ahead and give us 880 joules minus 0.5 times 200 times 19.4 gives us 1,940 joules. So our final change in rotational kinetic energy, it is 800 minus 1940, gives us an answer of negative 1,140 joules of energy lost. All right, that takes care of part B of example 24. This brings us to the end of our lesson, as well as the end of Unit 7. Thank you so much for watching.